Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is April 15, 2017. The title of this lecture is Forces and Moments Acting Upon a Rotating Propeller. The forces and moments acting upon a rotating propeller include centrifugal force, aerodynamic force, thrust bending force, drag bending force, gyroscopic precession, counter-torque, and rigidness-in-space. Here's a drawing that I put together that represents these forces and moments which act upon a rotating propeller. This here is a two-blade fixed-pitch propeller rotating counterclockwise. And of course at the root you have a higher blade angle of attack, and then it decreases in angle towards the tip, represented by the helical twist. When the blade is rotating counterclockwise, the airflow that's incurred against the lower blade surface, or the blade back, is causing a twisting moment in the opposite direction of the positive angle of attack, known as aerodynamic force. So the materials in the blade have to hold up against aerodynamic force, or the aerodynamic drag, which is opposing the positive angle of the rotating airfoils or blades. So that's the aerodynamic force, the opposition to the angle of attack caused by aerodynamic drag during rotation. The next is the thrust bending force. Just like on a fixed wing airplane, there is a moment in the form of thrust. In this case, since the blades or the wings are rotating, it's going to cause a bending force upward, or if we're looking at the propeller facing it, it's going to create a force in the form of bending force forward. Next is, if this propeller is on an airplane, we're facing the airplane forward, and the aerodynamic drag incurred during flight wants to push against the propeller faces. That would be represented by drag bending force wanting to bend the blades backwards, or rear. Next is the greatest force applied upon a rotating propeller, and that's the centrifugal force, the outward static force that wants to pull the blades apart from the root outward. So the materials of the blade have to hold up against enormous centrifugal force. If they don't, then these blades will be ripped off outward, causing them to go dynamic, and you don't want that to happen. Also, the centrifugal force is exploited in order to strengthen the rigid integrity of the blades, canceling out the bending forces. So you'll see some turbofan propeller blades on airliners, and they're actually set up with semi-rigid blade roots, and they'll kind of drag, but as the RPM increases, they tighten up outward from the centrifugal force. So the centrifugal force is also used to help with the rigid integrity of the blade structures by static tensile force outward. Next is the gyroscopic precession. If this propeller blade is rotating counterclockwise, and let's say we tipped it forward, it would actually not tip forward, it would tip to the left, because precession reaction moment takes place exactly 90 degrees in the direction of rotation where the initial tilting moment was applied. Next is the counter-torque. Since force is equal to mass times acceleration, we're dealing with angular acceleration counterclockwise multiplied times the mass of the propeller itself, causing a angular force in the direction of rotation, thus causing a angular reactionary force in the opposite direction, represented by counter-torque. So this torque would have to be dealt with and canceled out when used on a certain application. And then the last moment or force acting upon a rotating propeller is called rigidness-in-space. Since the RPM of the blades will cause a certain disk area to manifest due to the fact that the blade is in so many positions over such a small amount of time, the centrifugal force is somewhat equalized outward, causing this entire structure to become very rigid, and it's very hard to move. So if we apply this application on an airplane, if we're dealing with precession moments, let's say this is a propeller on an airplane, looking at it from the forward view, where the pilot is sitting here, we're looking at the pilot forward. If the pilot plans on rotating the airplane positive pitch to liftoff, it's the same as tilting this propeller forward, which will cause a yaw moment to the right. So unless he has enough of an angle of incidence on the vertical stabilizer mounting to cancel that out, it's called P factor, while getting to know the airplane's flight characteristics. If the P factor is limited, the pilot knows that when rotating positive pitch, the pilot will also have to hit a little bit of left rudder to cancel that right moment caused by the precession during the climb. And also, if the pilot was, let's say, flying level and he or she yawed left, it would be like tipping this propeller to the right, and since the precession would react 90 degrees in the direction of rotation, it'd actually get a pitch moment positive. So while hitting the left pedal input, you'd also have to push forward on the yoke to get a little bit of negative pitch moment downward to cancel that out. And so a lot of structural designers of airplanes will keep that in mind and place certain structural incidences into the flight structures to create inherent stability. But that's just an example of how precession affects a propeller on an airplane, especially if it's a single propeller. Next, the counter torque. If this was an airplane, you would have much longer wings outward, which make it hard for the counter torque to really cause the airplane to roll to the left. But even if it did, even if you had a much longer propeller, you also have control on the ailerons to turn the yoke a little bit to the right to cancel that torque out. But this torque is inherent, but it's also more dominant during the RPM changes, because then acceleration is changed in the RPM on a rotational plane. And so there's a little bit of a counter torque moment that takes place. And this is applicable to anything that rotates, whether it's a flywheel on a car or any type of rotating structure. The mounts have to have a torque arm to cancel some of that torque out and absorb it on a flexible torque arm, so the mounts don't fall apart from constant torque stresses. And then we have rigidness in space. Like if you have quite a large propeller, going at too high RPMs will actually cause the rigidness of space to take dominance, and that will be kind of hard to steer that given airplane. But rigidness in space is seen also with the bicycle wheel. When you rotate it fast enough, it wants to stand up. Also on a gyroscope that stands up by itself, when it's rotating at higher or high RPMs, it's going to elicit a rigidness in space that causes the gyroscope to stand up on its own. And like I said, it's from all the centrifugal force vectors that are almost happening simultaneously at higher RPMs. It wants to tighten up and make the rotating mass very rigid. We also see this in projectiles. the rifling inside rifle barrels spins around and causes the projectile to remain relatively straight, only affected by crosswinds and gravity drop on its trajectory. Also see this in American NFL football, where the football players, when they throw a football that is streamline shaped, it travels relatively straight on its parabolic trajectory because of the rotation and the spin. And the reason for that is because of rigidness in space. So anything that rotates, whether it's aerodynamic applications or not, whether it is a rotating disc or a rotating flywheel or a rotating sphere or a BB gun round the rotating ball bearing, it will always have centrifugal force wanting to pull the material out from its center of rotation equally on each half section outward on the rotating plane due to centrifugal force. Whether it be a flywheel rotating, it's going to have centrifugal force wanting to pull the flywheel plate apart, and that's why the materials are reinforced for that. Also, all rotating masses will elicit gyroscopic precession, because if this was a flywheel on a car engine and you were to tip it forward, you would get a moment to the right. So anything that rotates, you're going to have centrifugal force, you're going to have precession reaction, and you're going to have counter torque. But when we use the rotating mass in an aerodynamic application such as a propeller, we also then have aerodynamic force, thrust bending force, and drag bending force. And these are somewhat reinforced and stabilized through centrifugal force, although the aerodynamic force also is intensified due to the centrifugal force wanting to pull it out, causing the causing an inclination of negative pitch to incur. So that's why the structural materials have to hold up to all of these different forces, especially the aerodynamic force and the centrifugal force wanting to pull the blade apart and also decrease the pitch of the AOA, offsetting the properties and the specifications of the given propeller blade. So it cannot deform due to centrifugal force and aerodynamic force. As for helicopters, gyroscopic precession, this is exploited for main rotor tilt control, because on a helicopter you have a collective cyclic control at the main rotor swash plate as well as an anti-torque rotor on a conventional helicopter. And so if this was a helicopter rotor rotating counterclockwise looking down on it, and the pilot wanted to have a forward tilt, this means the applied force would have to happen to the right at this point here. But for that to happen, there would have to be a cyclic pitch control, which causes the pitch to increase more on the left advancing blade higher than the retreating blade, causing a tilt to the right applied moment, thus causing a precession reaction fork. So that is all in the swash plate scissor links on a rotary wing or helicopter application, which exploits gyroscopic precession for main rotor tilt control. Also, there will be a counter torque in the equal and opposite direction. So when the pilot of a helicopter accesses the collective control, they're going to collect an equal amount of pitch on both blades. Looks like that little parking brake lever in between the pilot and the co-pilot seat. That's the collective. And when the helicopter pilot pulls up on that, this will equally change the pitch on a constant RPM application, causing the helicopter to lift off and hover. But since there will be initially a counter torque moment causing the helicopter to yaw right, the pilot intuitively knows right when the liftoff and hover take place to push a little on the left anti-torque rudder pedal, causing the pitch on the anti-torque rotor to propel airflow more to the left, causing the tail to yaw to the right to cancel that torque out. So that would be airplane and helicopter applications, where the helicopter likes to exploit the precession and also the torque to an extent, because you're going to trim the anti-torque pedal inputs a little bit in the cancellation of the counter torque going right yaw, but you're actually going to use a little bit of the torque that is naturally existing to have a little bit of left yaw on the turns, along with a roll moment to coordinate that, just like on a fixed wing airplane. So the precession is kind of something that is problematic and needs to be corrected on the airplane. The torque is not too bad on the airplane with the wings, but on a helicopter they take advantage of precession for steering, and on one end torque has to be canceled in the opposite of the rotor rotation direction, whereas it helps a little bit in the natural torque or counter torque reaction for steering on another axis or another direction of the yaw. Okay, so we got the helicopter, we got the airplane. Last but very important application to cover, knowing the forces and moments on a rotating wing or a propeller, is the application of counter or contra-rotating propellers. And like with drones, they will electrically control the RPM to be equal and opposite through computer controls and electronic speed control. But with something larger like a actual airplane that has counter-rotating propellers, you're always going to have a gas engine, and it's kind of hard to individually control every engine's RPM equal and opposite. You need to have an equal and opposite counter-rotation of the propeller to take advantage of counter or contra-rotating propeller application. And so therefore, let's say this is the front of an airplane that has counter-rotating propellers. So let's say this is the right propeller looking at the plane, and we have another one just like this, a left propeller. So the right propeller is rotating counterclockwise, the left propeller is rotating clockwise. So now, because the right propeller is rotating counterclockwise, let's say the pilot climbs by positive pitch rotation. The right propeller is going to have a precession moment tilting it to the right, causing a right yaw. If the climb is positive angle, it's going to tip or cause a moment to tip the right propeller forward, causing a right yaw. But the other propeller is rotating clockwise, equal and opposite RPM, and causing a left moment. So what happens with equal and opposite rotating, contra-rotating propellers is that the precession is completely canceled out. You have an equal precession, equal and opposite precession between both propellers, causing them to cancel out the precession. So if this was two counter-rotating propellers, and then we have a central power plant with contra-rotating transmission drive shafts going from the contra-rotating transmission, clutch, and engine, and then the output drive would rotate, the right propeller output drive would rotate counterclockwise, the left propeller output drive would rotate clockwise, equal and opposite. Then when the airplane does a climb, the right propeller would cause a yaw moment right, the left propeller would cause a yaw moment left, canceling out the precession. Also, the counter torque would also be canceled out too, because it would be an equal amount of counter torque in the opposite direction. So if, let's say, this was flying level and you had so many foot-pounds of torque counterclockwise, it would also equal to so many foot-pounds of torque clockwise on the other propeller, canceling out the torque. So that's the advantage of having contra-rotating propellers, is that you can cancel out the precession and the torque, but do know that if you have large span contra-rotating propellers, the rigidness in space gets a little intense, especially at higher RPMs. And pilots do report having a little hard time actually getting a response out of the controls for maximum control authority. So, once you get level, you can drop your power or your RPM relatively lower, because you have two sources of propulsion. Rotating blades or propellers equal and opposite in RPM. So if you had 3,000 RPM counterclockwise, you would have exactly 3,000 RPM clockwise on the other propeller. So you would be able to just climb freely without having any problems with precession and torque. But let's say this is a single propeller, and let's say it's flying level on an airplane, we're facing the airplane, and let's say the pilot put a right input in. This would be the same as tilting this propeller disc to the left, and since it's rotating counterclockwise, you'd actually get a moment backwards, which is represented by negative pitch if this was an airplane looking at it forward. So the pilot, knowing the airplane, the certain equipment they're working with and its limitations, would know that if they were going to right rudder without coordinating the ailerons on the bank, they were just going to hit a little right rudder to line up somewhere. They would get a little bit of a down moment, and they would just pull back on the yoke a little bit to induce a little positive pitch to cancel that down moment. So you can see the logic behind it. So precession is existing in anything that rotates. Same thing as torque. Same thing with rigidness in space. But if it happens to be an aerodynamic application, then you also have the three forces. You also have four forces inherent to all rotating masses: centrifugal force, precession, torque, and rigidness in space. But then you have three more applying aerodynamics, affecting aerodynamic structures in rotation, and that would be the thrust bending force, drag bending force if in forward flight, and then the aerodynamic force, which wants to oppose the inherent structural AOA of the blades because of aerodynamic drag. So these are the forces and moments that are acting upon a propeller in whatever application, whether it's rotary wing for helicopters or propellers on airplanes. And then these are the forces, and then if you create another counter-rotating propeller, then all of these forces or moments applicable to precession and torque are also going to be canceled out, provided you can rotate these at equal and opposite RPM. Now if you have a little bit more RPM compared to the other propeller, let's say something happens and this right propeller is rotating a few RPMs faster than the left, you can see that the counter torque would be more going on a left roll. So you'd know there's an issue. Now if this was a quadcopter, a multi-rotor, you'd have four rotating propellers, and because they're computer controlled electronics with constant current lithium polymer going into a power distribution board and then into a electronic speed controller computing, the electrons would be metered in such a manner that all four would rotate in perfect and equal opposite rotation. So if you put one propeller, let's say this is the front of the quadcopter, you have two props, equal and opposite rotation, and then you have two props in the rear, equal and opposite. That means all four are going to be equal and opposite in rotation. So let's say it's fixed pitch, you don't have any variable blade pitch slash plate on it, just something with few moving parts. So you'd have computer control, so when you put the throttle in, it would rotate these all equally, you'd get liftoff, and if you wanted to tilt forward, you'd have a higher RPM in the two rear propellers, canceling each other out, so there's no torque and no precession going on, and this would cause a tail lift greater than the front lift, causing the tilt to happen. And that's applicable to the roll and as well as the pitch. But when it comes to yaw, you would have to slow down one of these rotors and or change the pitch to keep the lift equal while taking advantage and exploiting the torque for yaw control. So there's all sorts of applications that can be implemented once the physics of the forces and moments are understood on a rotating propeller. So these are the 7 moments and forces applicable to a propeller in rotation. Thanks for watching this video. Like and subscribe, and have a great day.